Good morning to all. Myself, M.Ramya, Assistant Professor in working in ECE Electronics and Communication Engineering Department in Erode Sengunthar Engineering College. Today, I am going to handle transmission lines and waveguides subject. So, in our college, we are conducting GATE coaching class for SC/ST students under the scheme of AICTE PRERANA. So, what are the importance of GATE means? GATE is a graduate aptitude test in engineering. So GATE is an all India examination that preliminary test that comprehensive understanding of various undergraduate programs in engineering and science. So what are the importance of GATE exam means? The GATE score of a candidate reflects his relative performance level. The score is used for admission to various postgraduate education programs such as Master of Engineering, Master of Technology, or Doctor of Philosophy at higher education institutes in India, with financial assistance provided by the MHRD and other government agencies. The GATE scores are also being used by several Indian public sector undertakings for recruiting graduate engineers in entry level positions. So, this is the importance of GATE exams. So next we are going to handle the today's session we're going to see about transmission lines equations. So generally, what are the basic principle of transmission lines means? Transmission line is used in radio frequency engineering. It is a specialized cable or other structure designed to conduct alternating current of radio frequency, that is current with a frequency high enough that their wave nature must be taken into account. So transmission lines are used for purpose such as connecting radio transmitters and receivers with their antennas, distributing television cables, trunk lines, routing calls between television switching centers, computer network connections, and high speed data buses. So these are the importance of transmission lines. So generally, transmission lines is used to propagate the electromagnetic wave. For example, this is a transmitter, this is an antenna. To connect the transmitter and antenna, in between there is a cable. That cable is called transmission line. So next, the fundamentals of transmission line. There are two types of commonly used transmission lines. One is coaxial cable, another one is an parallel wire transmission line. The another name of coaxial cable is balanced line, and parallel wire transmission another name is balanced line. The balanced line means is made of two parallel conductors spaced from one another by a distance of 1.2 inches up to several inches. So insulating spaces may be used in the wires to be separated, that is dielectric material. So the unbalanced line has a one conductor at the center and outer buried conductor which is grounded. That is coaxial cable. These two cables are mostly used in the communication. This is the example of this is a structure view of coaxial cable. So the coaxial is a type of electrical cable consisting of inner connector surrounded by a concentrating conducting shield with the two separated by a dielectric. Many coaxial cable have a protective outer jacket. So next, the coaxial cable carries a signal of high frequency range from 100 kilohertz to 500 megahertz. So next, applications of coaxial cable. Coaxial cable is used with unbalanced properties are needed as an interconnection of broadcast transmitter to its ground antenna. It is also employed at ultra high frequency and microwave frequencies to avoid risk of radiation from the transmission line itself. In the transmission line, the electromagnetic only want to propagate. It does not radiate in the transmission line. So next, it mainly used in telephone cables, cable television system for cable connection, local area network for computers. So this is the another example, the connection between dish antenna and TV receiver. So this is a comparison between parallel wire transmission line and coaxial table. First parameter we want to concentrate type of transmission line. So the parallel wire is balanced line, the coaxial cable is unbalanced line. So next structure. So the parallel wire line is there is a two plates, in between the two plates it having a dielectric material. But in the coaxial cable, it is a inner conductor, outer conductor. The frequency range, the parallel wire transmission line used in hertz to few megahertz, but coaxial cable used at ultra high frequency, microwave frequency range up to 100 kilohertz to 500 megahertz. So next, applications of parallel wire transmission line. It is mainly used in Yagyu array antenna to, in early days we used the TV receiver. Next, rhombic antenna to high frequency transmitter. The coaxial cable, it is mainly used in cable TV network, telephone lines, this antenna to TV receivers. So this is a comparison between parallel wire line and coaxial cable. So next, in this session, we're going to consider only the two-wire parallel transmission line. So in the transmission line having a, already we seen two conducting plates. In between the conducting plates, it's have a dielectric. So that parallel wire having a series inductance and resistance. The parallelly we having a capacitance and conductance. So this is a equivalent circuit of transmission line. So for is the RF equivalent circuit. In that the R and C is R and G is a in high frequency we neglect resistance value and conductance value. So we want to concentrate only L and C. So what are the primary constants of transmission line? The consider a long transmission line consisting of two parallel uniform conductors carrying current. There is a magnetic field around the conductors and voltage drop along them. So the magnetic field existence of magnetic field indicates that the line having a series inductance and the voltage drop indicates the presence of series resistor. So next, with the effect of primary constant on a transmission line, the primary constant taken into account both the forward and return lines. They are constant in that they don't vary with the voltage or current. However, they are frequency dependent to some extent. The series resistance are increased with respect to the frequency. As a result, the effect of skin effect. So next, inductance. So inductance is almost independent of frequency for open lines, but tends to decrease with the increasing frequency for screened cables. So the capacitance C is almost independent of frequency, whereas G tends to increase with the frequency of increasing dielectric losses with increase in frequency. So next, the voltage applied across the conductor produces an electric field between the conductor and charge them. This shows that the lines have shunt capacitance and shunt conductance. So there are four main primary constants in the parallel wire transmission lines, that is resistance R, conductance G, inductance L and capacitance C are called primary constant of transmission lines. Next, the R is series resistance. The unit is ohms per unit length. L is the series inductance, Henry's per unit length. C is the shunt capacitance. So shunt capacitance, Faradays per unit length. And G, shunt conductance, the susceptance per unit length. So next, the primary constant of your transmission lines is resistance, inductance, capacitance, and conductance. But the secondary constants of your transmission lines is characteristics impedance and propagation constant. These are the two important parameters it is used in the transmission line. It is used to analyze the transmission line. So first, what is the characteristics impedance? Characteristics impedance of a transmission line, that is a symbol of Z0, is the impedance measured at the input of this line when its line is infinite. That is, the impedance is measured at the input of this line when the length is infinite length of the transmission line. So any circuit that consists of series and shunt impedance must have an input impedance. So for the transmission line, this input impedance will depend on the type of length, its length and termination at the far end. So the method of calculation, how you going to calculate the characteristics impedance means, if a line has a infinite length, all the power feed into it, it will be absorbed. because the voltage drop across the inductance and leakage current through capacitance. So we know that R equal to V by I. So the Z not equal to V by I. That is the infinite lines. We have a characteristics impedance. So next we going to calculate the characteristics impedance from filter theory. The characteristics of a iterative circuit consist of series and shunt elements is given by Z not equal to root of Z by Y. The Z equal to series impedance, Y equal to shunt admittance. So the impedance Z, series impedance Z equal to R plus J omega L. The shunt admittance is defined by G equal to Y equal to G plus J omega C. So we know that Z not equal to root of Z by Y. So we going to replace in this equation Z not equal to Z equal to replaced by R plus J omega L. Y is replaced by G plus J omega C. So the Z not equal to root of R plus J omega L divided by root of G plus J omega C. This equation shows the characteristics impedance of a transmission line. It may be a complex one. Complex one means R plus JX. That means at high frequency, we're going to regulate R and G. Why means it high frequency, omega should be high. That is omega equal to 2 pi f. F should be we going to increase. So when we compare the value of omega L and R should be neglected. The same is omega C is high when compared to the G. So at high frequency, we're going to neglect R value and G value. So in we substitute R equal to 0 in the equation Z naught. That same the G equal to 0. The equation becomes Z naught equal to root of J omega L divided by J omega C. So we can to cancel that J omega divided by J omega. We will get Z naught equal to root of L by C. L is measured in Henry per meter and capacitance is measured, C is measured by Faraday per meter. At low frequency, the omega L is very small when compared to the R. The same thing, G is very small when compared to the omega C. So substitute omega L is 0, omega C is 0. The impedance, characteristic impedance equation becomes Z not equal to root of R plus 0, R plus 0 divided by root of G plus 0. So we will get Z not equal to root of R by G. So the characteristic impedance value is varies from 200 to 600 ohm. So at high frequency Z not equal to root of R, root of L by C, root C. At low frequency Z not equal to root of R divided by root G. So the characteristic impedance value varies from 200 to 600 ohm. So what are the advantage and disadvantage of transmission lines? The main advantage is it is a simple construction. We easily construct the transmission line. It is a flexible one, highly mechanical strength, and the cost is very, very less. So what are the disadvantages of transmission lines means it increases in power loss with the frequency is increased. It cannot handle high voltages. So this is the advantage and disadvantages of transmission lines. So what are the losses in the transmission lines means there are three losses it occur in mainly occurred in the transmission lines in which energy applied to a transmission line may be dissipated before reaching the load. When we pass the electromagnetic from source to load, in between there are some losses. The losses are radiation loss, conductor heating loss, dielectric heating loss. First one, radiation loss. The radiation loss occur because a transmission line may act as an antenna. So antenna only they radiate the electromagnetic wave. The transmission line role is it want to propagate the electromagnetic wave. The transmission line won't radiate. So some cases the radiation losses occur. That means the transmission antenna, the transmission line radiates. So the radiation losses occur because a transmission line act as a antenna. If the separation between conductor is an appreciable fraction of wavelength, this occurs more to parallel wire lines than a coaxial lines. Radiation losses increases with the frequency for a given transmission line. So next, when the radiation loss will occur, the transmission line act as an antenna only. The radiation loss will occur. That means it bend. The transmission line will bend. It act as an antenna. So next, conductor heating loss. The conductor heating loss is proportional to the current and therefore inversely proportional to the characteristic impedance. So it is also increase the skin effect. Next one is a dielectric heating loss. The dielectric heating is proportional to the voltage across the dielectric and hence inversely proportional to the characteristic impedance for any power transmitted. This loss also increase with the frequency. So for a given dielectric medium. So the conductor loss and dielectric loss are both are dependent on the frequency. For air is a perfect dielectric medium. For air, dielectric heating means negligible. For the coaxial lines at 1 gigahertz, these loss may vary from 20 decibel to 100. Okay. So next one is a standing waves. What is meant by standing waves? Standing waves is also known as stationary wave. Is a wave which oscillates in time but whose peak amplitude profile does not move in space. The peak wave amplitude of the wave oscillation at any point in space is a constant with time, and the oscillation at different points throughout the wave in space in phase. The location at which the obstacle value of the absolute value of the amplitude is minimum are called nodes, and the location where the absolute value of the amplitude is minimum are called antinodes. So another name of standing waves is another name stationary waves. The phenomena can occur because the medium is moving in the opposite direction to the wave, or it can arise in a stationary medium as a result of interference between two waves traveling in opposite direction. The most common cause of standing waves is the phenomena of resonance, in which standing waves occur inside a conductor due to the interference between waves reflected back and forth at the resonant frequency. So simply we saying the standing waves is the forward and reflected waves on the incorrectly terminated transmission line produce an interference pattern known as standing wave. Example, when the source impedance not equal to the characteristic impedance in that time, the when we pass the signal to the source to receiver, the characteristic impedance is not equal to the load impedance means some amount of the power is reflected back to the source, that is called standing waves. Stand that in the time the standing wave will occur. The standing wave is a unique distribution of voltage and current along the transmission line that is not terminated in its characteristic impedance. When the load impedance not equal to the characteristic impedance means that standing wave will produced. The concept of standing wave can be best understood by considering the two cases of impedance mismatch at load or the antenna. The load is always an antenna. So there are two cases. One is open circuited, another one is in short circuited. First, we consider the open circuited. So this is a source that the end at the load it is a short circuited. At the short circuited, we know that the voltage is minimum, the current is maximum. So this is the voltage is minimum, the current is maximum. In that we consider the 2 points node and antinodes. Okay. Next one is N. The waveform below the transmission line shows the voltage and current at each point on the line. We can measure this voltage and current at each point with the help of multimeter. As when the voltage is zero while the current is maximum. See the figure here. The voltage is minimum at the point the current is maximum. The dotted line represents the current waveform. So this line represents the voltage waveform. When the voltage is minimum, the current is maximum in the short circuited. So there is a two waves propagated in the opposite direction that produces a standing waves. All the power is reflected back to the source. Next one, the voltage and current variation distribute themselves according to the wavelength of the signal. The pattern repeats of every one half of wavelength. The voltage and current levels at the source will be dependent on the signal wavelength and actual line. So next in the open load, the voltage is maximum, the current is minimum. Okay. So next, the open circuits means there is an infinite impedance, so that the voltage at the end of the line is maximum, the current is zero. All the energy are reflected back. All the energy is reflected back, thereby setting up this stationary pattern. So practically, transmission line won't have a short or open circuited condition. Instead, the load impedance will not be equal to the transmission line that is characteristic impedance. So the practically we won't make the open circuit and short circuit conditions, but some applications the your source impedance not equal to the load impedance. For example, we will consider the antenna impedance and the transmitter impedance is not equal, means the source the some amount of the power back to the source. So that is this is the practical conditions where the standing waves will produce. That is a mismatch. When will mismatch will occur? The antenna will have reactive component, either capacitive or inductive, as well as it is resistance. The mismatch will produce standing waves, but with less amplitude. The distortion is shown in the figure. So there are two types of lines: resonant line and non-resonant line. Resonant line means the line is terminated by other characteristic impedance, is called a resonant line. Non-resonant line means A non-resonant line means the line is terminated in its own characteristic impedance, is called a non-resonant line. So next, another parameter, reflection. What is meant by reflection? The reflection of energy source or energy occurs when there is an impedance irregularity. That means the impedance value, consider the one transmission line, the length of 10 centimeter. At 1 centimeter, the impedance value is or one thing. At the 5 centimeter, the impedance value is varied. That is a impedance irregularity when the primary constant of the line are not uniform along the line, or the terminated impedance at the far end is different. That is resistance. The primary constants are resistance, capacitance, inductance values differ. This reflection will be maximum when the line is open circuited, that is ZR equal to infinity. When the reflection is maximum, the open circuited condition. This reflection will be negligible or almost zero when the line is short circuited. That is, the receiving end impedance is zero. This reflection normally is undesirable on transmission line. If a line is terminated by its characteristic impedance, means that line is non-resonant line. So the reflection coefficient is zero. That is, if ZR not equal to Z naught, means the equation should be Z naught equal to ZR minus Z naught divided by ZR plus Z naught. So if ZR equal to Z naught, means there is row standing waves is already seen. If ZR not equal to Z mean, means some of the power is absorbed in the load and the rest is reflected back. So this is the example. Some of the power is again reflected back. So the standing waves is two set of traveling waves traveling in opposite direction set up an interference pattern known as standing waves. So the already we seen. Next we going to see about standing wave ratio. The ratio of maximum and minimum magnitude of voltage or current on the line having a standing wave is called a standing wave ratio. That is, the magnitude of standing waves on a transmission line is determined by the ratio of maximum current to the minimum current along the line. So the standing wave ratio equal to V max by V min divided equal to, or I max by I min. That is maximum voltage divided by minimum voltage. So we already seen the properly terminated transmission line ZL equal to Z naught. So the load impedance equal to the characteristic impedance means there is no reflection takes place. So this is the ideal condition. In this conditions, Vmax equal to Vmin. So Vmax equal to Vmin means S equal S becomes the standing wave ratio is taken as S. So Vmax equal to Vmin means this is equal to 1. So there's a Vmax equal to Vmin means S standing wave ratio equal to 1. So next, reflection coefficient. If a finite piece of line is terminated in impedance not equal to the characteristic impedance, then the sum of the power will be absorbed by the termination and remaining power will be reflected towards source. If VA is considered as a incident voltage and VR we consider as a reflected voltage along the line. So another definition is reflection coefficient. The reflection coefficient is defined as the ratio of reflected voltage to the incident voltage is called reflection coefficient. Is a K is equal to VR by VI, or K is equal to incident current divided reflected current divided by incident current. So if the line is terminated by its characteristic impedance, there is no reflection, that K becomes 0. K becomes 0. If the line either open circuited or short circuited, definitely reflection will occur and standing wave will produced. So that condition is ZL not equal to Z naught. The VI and VR is same. In this case, K equal to 1. So the voltage standing wave ratio, already seen Vmax by Vmin. The Vmax equal to modulus of the Vi plus modulus of Vr. The Vi is the RMS value of incident voltage. Vr is the RMS value of reflected voltage. So the standing wave ratio is Vmax by Vmin. So the Vmax is replaced by modulus of Vi plus modulus of Vr. The V minimum is replaced by modulus of Vi minus modulus of Vr. So we will substitute the standing wave ratio equation Vmax Vmin value. We will get 1 Vi plus Vr divided by Vi minus Vr. In this equation, we taken out Vi is the common term. We will get Vi into 1 plus here Vr divided by the Vi comes under denominator divided by the denominator term also we taken Vi is a common term. We will get Vi into 1 minus Vr by Vi. So the commonly VI is cancelled. We will get 1 plus VR modulus of VR by VI divided by 1 minus VR by VI. We know that the reflection coefficient K is defined by VR by VI. So we replaced VR by VI equal to K. So we will get standing wave ratio equal to 1 plus modulus of K divided by 1 minus modulus of K. So this is the relationship between standing wave ratio and reflection coefficient. So next, we will write VSWR minus 1 divided by VSWR plus 1. So equal to 1. We know that VSWR is 1 plus modulus of K. So divided by 1 minus modulus of K. Here wrote 1 plus modulus of K divided by 1 minus modulus of K minus 1 divided by 1 plus modulus of K divided by 1 minus modulus of K plus 1. We will take one denominator term is common, that is cancelled. We will get 1 plus modulus of K minus 1 plus modulus of K divided by 1 plus modulus of K plus 1 minus modulus of K. Here the numerator, the plus 1 minus 1 will be cancelled. The modulus of K plus modulus of K becomes 2 into modulus of K divided by in the denominator term. We will get 1 plus 1 equal to the plus modulus of K, the minus modulus of K cancelled. We will get 2. So the equation becomes 2 modulus of K divided by 2. So the modulus of K becomes VSWR minus 1 divided by VSWR plus 1. The 2 is cancelled. So the VSWR is taken as yes, that is standing wave ratio. So the relationship between reflection coefficient and standing wave ratio becomes the modulus of K equal to S minus 1 divided by S plus 1. We also write in terms of impedance Z K equal to ZR minus Z naught divided by ZR plus Z naught. Next, quarter wavelength and half wavelength. The transmission lines the way generally that standing wave will produce. The how we going to minimize the standing waves, that is we going to see the next in this session. The transmission lines are exactly quarter wavelength. Quarter wavelength means lambda by 4. That is wavelength is lambda, the quarter means lambda by 4, or a half wavelength, that is lambda by 2. Along have some impedance transforming properties, that is impedance matching. For this purpose they are used at radio frequencies. So the quarter wave impedance transformer, written as lambda by impedance transformer, is a transmission line or waveguide used in electrical engineering of length of one quarter wave. Is terminated with some known impedance. It represents its input, the dual of the impedance when with which it is terminated. Okay. So next, it is a similar concept to a stub, whereas a stub is determined terminated in a short or open circuit, and the length is chosen as to produce the required impedance. But in the lambda by 4 transformer is the another way around. It is a predetermined length and the termination designed to produce the required impedance. The relationship between the characteristic impedance is at naught and the input impedance is at 10 and load impedance is Z10 divided by Z naught equal to Z naught divided by ZL. So the operation of the quarter wave lines is quarter wave transformer are the in the standing waves on a transformer with open circuited load and short circuited load. So the quarter wave length away from the open circuit, the current and voltage or oscillations are exactly the same as at short circuit and vice versa. The, this reflects that sorry, this reflects that fact the open circuit is at r equal to infinity is a dual to short circuit is at not equal to 0. This is consider the below diagram. So this is the length of the transmission line is lambda by 4. Okay. So next, the equation represents the very important and fundamental relationship between this. Unless the and unless the load is resistive and is equal to the characteristic impedance of the line, the standing waves of voltage and current are set up along with the line with a node and antinode repetition rate of lambda by 4. Node and antinode means voltage maximum and minimum is occur with the process of lambda by 4. The relation is called reflective impedance, means the quarter wave length reflects the opposite to of its load impedance. That is a impedance inversion. So note that the voltage and current minima are not zero. The load is not a short circuit, so that the standing wave is not a infinite. The current nodes are separated from the voltage nodes by a distance of lambda by 4. At point A, at the point A, the current is minimum. The current is minimum and that is voltage is maximum. The maximum is antinode, the minimum is node. The line is impedance, the line impedance is high. So because the node represents the minimum. So consider the point A. The node this point, the current is minimum, the voltage current is the voltage is minimum, the current is maximum. So the impedance is high. At the point B, the current is antinode, voltage is node. It is inverse, the impedance is low. So the equation is already seen ZS by Z naught equal to Z naught by ZS. So the ZS by Z naught is replaced by ZS, ZL by Z naught is replaced by ZL. So the equation becomes ZS is equal to ZL. The quarter wave transformer has a length of lambda by 4 at only one frequency because lambda equal to C by F. So the frequency, it is a frequency dependent one. It is a highly frequency dependent and this respect is similar to the high Q tuned circuit. The practical behavior of a transmission line transformer and ordinary tuned transformer is identical but the difference in construction. So the quarter wave transformer used as a filter, example the series inductance and capacitance, parallel inductance and capacitance. It is used to prevent unwanted frequencies from reaching the load such as antenna. If impedance matching is required for broadband, the transformer must be constructed with high resistance wire to reduce the Q, thereby increasing the bandwidth. So next, These are some line sections equal to the LC equivalent circuit. The lambda by 4 length, the equivalent circuit is either parallel LC circuit, where it is a short circuited, it is a series LC circuit. The less than the circuit, there is a pure inductive, either pure capacitive. This is the equivalent circuit of LC circuit of quarter wave length. If the frequency of operation is reduced, then there is a reduction in shunt inductive reactance and increase in shunt capacitive reactance. The inductive current predominates and the impedance current circuit is purely inductive. Now, the same piece at the new frequency is less than the lambda by 4 length. Since how the wavelength is greater than the length of the line is unchanged. We have an important property, that is a short circuited line less than the lambda by 4 long appear as a purely capacitance. So next, impedance matching. We're going to match source impedance equal to the load impedance. We're going to place the some stub in between them. That is a impedance matching. We're going to match source impedance and load impedance. The best way to prevent a mismatch between the antenna and transmission lines in a correct design. But practically mismatch occurs. The antenna resistance may be other than the characteristic impedance of the line. Definitely the standing wave will produce. To solve this problem, we're going to insert a stub between load and source impedance. Otherwise, we're going to insert a balloon, that is balanced to unbalanced transformer, that is LC, reality, or pi circuit network. These circuits will make the transmitter to behave properly but will not reduce the standing wave ratio on the transmission line. Stub. It is a possible to connect sections of open or short circuited line known as stub. The stub means that open or short circuited line, small length lines. The length will be varied, and we're going to place a low stub from the we want to find location of the stub, length of the stub. And we want to minimize the reflection. This match with the help of tuning stub or stub is called stub matching, and it has the following advantages. Length and characteristic impedance does not change mechanically. It is possible to add adjustable susceptance in shunt with the line. There are two types of stub matching: single stub matching and double stub matching. Single stub matching means we're going to place, for example, consider this transmission line. This is a source, this is a load. If the load impedance not equal to the characteristic impedance, the reflection will take place. We want to overcome this problem. We're going to place stub in between the lines. So we want to find the length of the stub and the location of the stub. Then only the load impedance equal to the characteristic impedance. The length of the stub and location of the stub only determine the load impedance. Load impedance equal to the source impedance. So the main element of this transformer is a shorted circuited section of a line whose open end is connected to the main line at a particular distance from the load end. So this is that we already told load impedance, sorry, length of the stub and location of the stub we want to find. Then only the load impedance equal to the source impedance. When where the input conductance at the point is equal to the characteristic conductance of the line, and the stub length is adjusted to provide a susceptance equal in value but opposite sign in sign to the input susceptance of the main line at the point, so that the total susceptance of the main line at this point is zero. The combination of stub and the line will thus present a conductance which is equal to the characteristic impedance of the line. The main length of the high frequency transmission will be matched. So next, what are the advantages and demerits of the single stub matching? So advantage of short circuited stub is less power radiation. The effective length variation is possible by shorting stub, and also the demerits of a single stub matching is the single stub matching suffers from the two main disadvantages, such as the range of terminating impedance which can be transferred is limited. Another one is this is usually only for fixed frequency, because the frequency varies, the position of the stub can be varied. So the length should be measured in only one terms of lambda. The lambda is dependent on the frequency. So only the frequency is varies. The stub length also varies. So next we are going to see about double stub matching. In double stub matching, that the but we're going to place two stubs. In that single stub matching, we placed only one stub, one short circuited stub. In that place, we're going to place two stubs. We have two locations, two length of the stubs. So mainly single stub matching is used in a practical. The rare occasion only the double stub matching is used. So another matching circuits is balloon. Balloon also called as balloon to balance to unbalanced transformer is a circuit element used to connect a balanced line to a unbalanced line. That is, it is used to connect an unbalanced line to a balanced antenna such as dipole. Here, the windings are associated with the balanced system is symmetrically arranged with respect to grounded, electrostatic shielded, so that the stake capacitance eventually present will not introduce the unbalanced. So there is an example. There is a TV receiver. This is the antenna. In between, we using a transmission line. If the antenna impedance is not equal to the TV receiver, the standing wave is produced. To avoid this standing wave, we going to insert the balloon. So the balloon is a inductance and capacitance only. So it is a consolidated. If the load in this much time we seen about the basics of trap two wire parallel transmission lines. What are the primary constant is used, that is R, L, G and C. What is the characteristic impedance? So is that not equal to root of Z by Y? At low frequency is that not equal to root of RG divided by root of R divided by root G? At high frequency the Z not becomes root of L by C. So next we going to see about the standing waves. S equal to V max by V min. Next reflection coefficient K. What is the relationship between reflection coefficient and standing waves? Next quarter wavelength, that is impedance matching. So what are the properties that are having the quarter wavelength? So relationship between Z naught and quarter wavelength ZL. So next we seen about the impedance matching, single step matching, double step matching and balloon. So is the final, if the transmission line in a quarter wave length, that is L equal to lambda by 4 length, the Zn equal to Z naught square divided by ZL. This is a very important formula. The input impedance of a quarter wave length Zn equal to Z naught square divided by ZL. Z naught square divided by ZL. For any length, Zn equal to ZL. That is the input impedance equal to the load impedance. If the transmission line have a half wavelength, the Zn equal to ZL. If the load is open circuited, then the load impedance is infinitive. The reflection coefficient tau or k equal to 1. If the load impedance is a short circuit, the ZL equal to 0, then tau equal to minus 1. So this is the next we're going to see about problems on transmission line equation. So they shown the some of the examples that are previously asked in gate questions. So first we want to going to see the load impedance is 200 ohm is to be matched to a 50 ohm lossless transmission line by using a quarter wave line, the characteristic impedance. So where the given is the ZL is at the trans Z is given. We want to find out characteristic impedance. We know that the formula for quarter wave line is Zn equal to Z naught squared divided by ZL. So we want to find out Z naught. So the Z naught equal to root of Zn into ZL. So Z naught squared equal to Zn into ZL. Zn is equal to 50 ohm. ZL equal to load impedance is equal to 200. So the Z naught squared equal to 50 into 200. So finally we got Z naught equal to 100 ohm. Next problem, a lossless transmission line having Z naught, that is 50 ohm characteristic impedance, and the length is lambda by 4. The lambda by 4 means quarter wave length is short circuited at one end and connected to an ideal voltage source of 1 volt at another end. So the current drawn, we want to find out the current. So for that we know that Z Zn equal to Z naught squared divided by ZL. So ZL equal to 0 for short circuited condition and the open circuited condition Z naught Zn equal to infinitive. So the current, we know that formula Is equal to Vs divided by Zn. When Zn equal to infinity, anything by infinity 0, so the current Is equal to 0. So next problem, the capacitance per unit length and the characteristic impedance of a lossless transmission lines are C and Z naught respectively. So the velocity of traveling wave on the transmission line is, we want to find out velocity. So what is the velocity formula? We know that lambda equal to C by F. So C equal to lambda into F. We consider C or V. So is that not equal to root of L by C? Why is that not equal to? We condition given is lossless transmission line. So is that not equal to root of L by C? Is that not squared equal to L by C? So we know for that formula V equal to 1 by root of LC. So we replaced L by Z not squared C. So the Z not squared C into C squared. So we get 1 by Z not C. The problem number 4, the transmission line of 50 ohm characteristic impedance is terminated with 100 ohm resistance. The minimum impedance measured on the line is equal to. So we gave in this sum, they gave Z naught, that is characteristic impedance 50 ohm, and the terminated impedance 100 ohm, that is ZL. We want to find out minimum impedance on the line is equal to. So Z naught equal to 50 ohm, ZL equal to 100 ohm. The minimum impedance is Z null greater than ZL. So Z naught, Z in formula is Z naught squared divided by, we want to divide by, sorry, Z naught squared divided by ZL. So the final answer is 25 ohm. So next sum, the magnitude of the open circuit and short circuited input impedance of a transmission lines are 100 ohm and 25 ohm respectively. But we want to find out the characteristic impedance of the line is. So open circuit and short circuited condition, is that not formula is root of ZOC into ZSC. Then some we gave short circuit impedance of the transmission line is 100 ohm. That ZSC equal to 100 ohm. So ZOC is equal to 100 ohm, ZSC equal to 50 ohm. The formula is Z not equal to root of ZSC into ZOC. So root of 100 into 25. So root of 100 into 20, we will write 10 into 5, we will get 50 ohm, that is characteristic impedance. Next, the transmission line has a characteristic impedance of 50 ohm and resistance R equal to 0.1 ohm per meter. If the line is distortionless line, so in the line is distortionless line, the attenuation constant we want to find out. So in the distortionless condition is LC equal to RG. The attenuation constant formula is R equal to root of RG. In this sum, they gave R value. They didn't provide G value. So next we want to provide G. So for that, the distortionless condition is LC equal to root of RG. Sorry, LC equal to RG is not equal to root of L by C. So R by G, alpha equal to R by G, we replace G by R into Z naught, we get R into Z naught. So R value is, we got when Z naught value is they given, so 0.150 in terms of Nepper per meter, 0.002 Neppers per meter. So next sum, the transmission line of a characteristic impedance is 50 ohm is terminated by 50 ohm load. When excited by a sinusoidal voltage source at 10 gigahertz, the phase difference between 2 points spaced 2 mm apart on this line is to be pi by 4. That is path difference. The phase, I want to find out phase velocity of a wave along the line is. First, we are given is that not equal to 50 ohm, is that L equal to 50 ohm, frequency f equal to 10 gigahertz, the spacing between is a path difference is 2 mm, and the phase difference is pi by 4. So the relationship between phase difference and path difference is beta L equal to 2 pi by lambda into path difference. The phase difference we replace pi by 4, 2 pi by lambda. The path difference is 2 mm, so that is 2 into 10 to the power minus 3. So from that equation, we will find lambda equal to 16 into 10 to the power minus 3 meter. So velocity formula is Vp equal to F into lambda, F on 10 gigahertz, and we will find the lambda value is 16 into 10 to the power minus 3. The finally we get the phase velocity is 1.6 into 10 to the power 8 meter per second. Next sum, the return loss of a device is to be 20 decibel. The voltage standing wave ratio and magnitude of a reflection coefficient or respectively. They provide only the reflection losses. We want to find out VSWR and magnitude of reflection coefficient. So we know that reflection law, written loss formula equal to minus 20 log of 1 row, otherwise 20 log of 1 by row. So we content to we otherwise we write minus 20 log of 10 row. The row is a reflection coefficient. We already called tau k. The row equal to 1, then the full reflection. So we replace reflection loss is 20 decibel. The relationship between VSWR and reflection coefficient is 1 plus k divided by 1 minus k. Either they wrote row. So we will find reflection standing wave ratio is 1.22. Next problem. The maximized power transfer, a lossless transmission line is to be matched to a resistive load impedance via lambda by 4 transformer as shown. We want to find out the characteristics impedance. So we know that Z not equal to root of Z in into ZL. In the sum they provide Z in value and ZL value. Substitute this value, we find out as the Z not value. So Z in equal to Z not squared divided by ZL. So Z not squared equal to Z in into ZL. Z not equal to root of Z in into ZL. Finally, we got 70.72 ohm. Next sum. The transmission line of a purely resistive characteristic impedance is terminated with a known load. The measurable value of VSWR on the line is equal to 2 and voltage minimum point is found to be at the load. The load impedance is then complex, purely capacitive, purely resistive, or purely inductive. We mean VMX occurs only the lossless transmission line. The load impedance is purely resistive. So last problem in a twin wire transmission line in air, that the adjacent voltage maximum are at 12.5 centimeter and 27.5 centimeter. The operating frequency is lambda by 2 equal to the distance 27.5 minus 12.5, we get 15 centimeter. So the lambda becomes 30 centimeter. So find out the velocity F equal to V by lambda. So we see a velocity of the electromagnetic wave, that is 3 into 10 to the power 8 meter per second. Lambda we found 30 into 10 to the power minus 2. Finally we got F equal to 1 gigahertz. So next problem. The characteristic impedance of a transmission line is 50 ohm. The input impedance of a open circuit line is ZOC equal to 100 plus J 150 ohm. What is the when the transmission line is short circuited, then the value of input impedance will be, so we know that Z not equal to root of ZOC into ZSC. So ZSC equal to Z naught squared divided by ZOC. So Z naught squared is 50. Z naught is 50. The finally we calculate that the Z naught ZSC equal to 7.69 minus J 11.54. So thank you. Thank you all. So next class we see about the stub matching problems. Thank you.